3b is about frequency distributions and histograms, which serve a similar function, which is basically to take a data set and give you a summarized version of it that's a little bit easier to interpret or understand. Because even if you just look at this, right, here's a data set right here, and just looking at it as it is, it's kind of hard to parse what's going on there. It would be much easier if it was a table or a graph, and that's what frequency distributions and histograms respectively are, right? A frequency distribution is a table, a histogram is a graph. So frequency distributions first, typically it is written out in table form. I've never really seen it where it wasn't. So what the frequency is, first of all, the frequency of a value is the number of times that it occurs in the data set. Sometimes rather than for individual values, this is done with intervals. So maybe not for something like example 1, but for something where maybe the data set is really, really big, and to go value by value wouldn't really make a lot of sense. Like, what if it's values that are like 4 or 5 significant figures, like, 1026.9, right? Like, you're not going to have each individual value listed in the table because the table would be ridiculously huge itself, right? That doesn't really fix your problem. So there you would use intervals, so that way you can shrink down the size of the table and get something a little more manageable. But what a frequency table shows is that it'll show the possible values of a variable along with their frequencies. So typically it's values in one column, frequencies in the next column, and that's exactly what we're going to end up with here. So with this first example, where here's our data set, the number of cars owned by a sample of 40 families, so there are 40 numbers in here. The reason that the 3s are in brick red and bold is just to tie those 3s to this 5 right here, which is also in brick red and bold. So the way that you would make the frequency table, or the frequency distribution table, I guess first of all, is to kind of comb through here and figure out what values show up. I mean, clearly they're all integers that are single digits, but we do have 0, right? Because there are a couple of them showing up. 1, 2, 3, 4, and 5, right? Because there's a 5 right there. And there's nothing bigger than 5. So our values for the number of cars, 0, 1, 2, 3, 4, and 5. And then to get the frequencies, you just count them up. So like for 0, there's a 0, and there's a 0, and there's a 0 right there. So there are 3 of them, so the frequency is 3. And then for 1, there are a whole bunch, and 2, there are a whole bunch. So 13 1s, 16 2s. The brick red 5 is to tie together these 3s. So like if you were going to count these up, you go, there's 1, 2, 3, 4, 5. So the frequency for 3 should be 5, right? That's how many 3s there are. Then there are 2 4s and then 1 5, and then that adds up correctly to 40. So there's the frequency distribution. You can have variants of this where instead of just the frequency, where that's a count, right? It's how many zeros there are, how many ones there are. What if instead of frequency, you wanted something like relative frequency? So what the difference is between frequency and relative frequency is frequency is just a count, where it's the number of times that value shows up. The relative frequency is the proportion of observations equal to that value. So it's like, of all the values in the data set, what proportion were 0, or what proportion were 1, or what proportion were 2, that kind of thing. So in order to get the relative frequency, you can just take the frequency and divide by the total number of observations, right? That'll switch it from being a count to a proportion. That's really all you have to do. And that's all I did here, right? And that's why, like for these first 2, I have it written out where it's the fraction first. Just to kind of point out that all these relative frequencies, is just taking the frequency and dividing by 40, since that's the total number of observations there. So for 0, the frequency was 3. The relative frequency should be 3 divided by 40, which is 0.075 as a decimal. And then for 1, the frequency is 13. 13 divided by 40 is 0.325. And then 16 divided by 40 for 2, well, that's 2/5, so that's 0.4. Right? It's that over and over and over again. And the relative frequencies should add up to 1, right? Because 1 in proportion form is 100% percent form. So should add up to 1. The next thing is cumulative frequency. This is a little bit different. So the cumulative frequency of a value It's sort of like a cumulative exam, right? Like if you have a class as a cumulative final, then that means it covers everything, right? It covers the new stuff and all the old stuff, right? Same idea, where with the cumulative frequency, it's the frequency of that value plus all the frequencies that came before, right? So just like a cumulative final. Another way to put it would be that it's the number of observations less than or equal to that particular value that you're looking at. So for 0, the frequency is 3. The cumulative frequency is also 3 because there's nothing before 0, right? That's the first possible value. But then for 1, the frequency is 13. The cumulative frequency is going to be 16 because you get the 13 for the 1 plus 3 before it for the 0. So that's where the 16 comes from. For 2, you have 16 2's, but then you also have these up here because 0 and 1 come before 2. So it's 3 plus 13 plus 16, which is 32. And then for 3, you've got 5 3's, so you've got that plus the previous 32, you get 37, right? And so forth. 2 4's plus the previous 37, you get 39. And then 1 5 plus the previous 39 all up here, right? So I guess if you had them all written out individually for 5, you'd have 3 plus 13 plus 16 plus 5 plus 2 plus 1, right? And then for 4, 3 plus 13 plus 16 plus 5 plus 2. But that's how cumulative frequency works, just like a cumulative final, right? That's probably the simplest way to understand that, or the easiest thing to tie it to. There is also a cumulative relative frequency, which just like the difference between frequency and relative frequency, the difference between cumulative frequency and cumulative relative frequency is just that this new one is in proportion for it. So you would just take the cumulative frequency and divide by 40 to get the cumulative relative frequency. So the proportion of observations in the data set less than or equal to the value in question, right? So for 0, we had a cumulative frequency of 3, cumulative relative frequency of 3 over 40. And then for 1, we had a cumulative frequency of 16, cumulative relative frequency of 16 over 40, which is 0.4, and so forth. The last one should be 1 because the cumulative frequency for the highest value, it's going to be the frequency of that value plus everything before it. That should be everything. So then when you divide by the total number of observations, you should be getting a 1 right there. Okay, so another thing that's worth pointing out here is that frequency distributions, a lot of times, instead of just showing individual values like the number of cars up here, a lot of times it is intervals rather than individual values. So like I said, this is when you don't just have a handful of possible values in your data set. You got lots and lots of them. And if that happens, then those intervals are called classes. So if I scroll down a little bit, like here are the classes. They're underneath the monthly salary heading, right? There's the first class, 2,600 to 2,799. There's the second class, 2,800 to 2,999, and so forth. And then each class should have a defined lower class limit and upper class limit. And those, I mean, I guess I can say that they're what you think they are. That's true, right? For the first class, the lower class limit's the 2,600 and the upper class limit's the 2,799, right? It's just the endpoints, basically. It's just a fancy terms for endpoints. That's really what we're talking about here. But I think that is actually worth writing out just off to the side here. So for the first class, we would have that the lower class limit is 2,600, which I guess it's in money, so I can put a $sign there. And then the upper class limit is 2,799. And it's the same for the rest of them, right? The second class, you're going to have a lower class limit of 2,800 and upper class limit of 2,999, right? And you can just keep going like all the way through that if you want. The other thing is the class width. So all the class widths should be the same rather than having like maybe the last one say some value and higher. And that does show up, like that's a thing that gets done. It's not the end of the world when that happens, but it makes graphing it very difficult. Right? If you're actually going to graph the thing and then turn a frequency table into a histogram, you want all the class widths to be the same. And since this section leads into histograms, then we're going to do it like that. So the class width, it's generally defined as a difference between two consecutive lower class limits, but you could certainly use upper class limits instead. You get the exact same thing. So for the class width, if I just use the first two classes here, and I just use those two lower class limits, it's 2800 minus 2600, which is 200, and you get 200 if you picked any two of them, right? If you pick the one that starts with 3200 and the one that starts with 3400, you're going to get 200 when you subtract, right? Same thing. You can pick whatever consecutive pair you want because the way this is set up, all the class widths are the same. Okay, good. That's the way it's supposed to work out. All right, the next thing is completing the rest of this table with the relative frequencies and the cumulative frequencies and all that. So this time, the total number of observations is 80. So to get the relative frequency, it's just the frequency divided by that, right? So for the first one, you'd have 8 divided by 80, which is 0.1. Then the next one is 11 divided by 80, which is, I gotta cheat and look, 0.1375. All right, then this one would be 17 out of 80, which is 0.2125. 19 out of 80 is 0.2375. Let's see, next, 10. Okay, that's an easy one, 125, since that's 1/8. Let's see, 6 is 0.075. 4, so 4 out of 80, it's the same thing as 1 out of 20, 0.05. And then 5 is 0.0625. All right, so there are the relative frequencies. The cumulative frequencies, well, that first class, there's nothing before it, so it's just 8. But then the one after it, you'd have the 11 for that class plus the 8 before it. So you have 8 plus 11, which is 19, right? Then 17, I guess you could say, well, it's the 19 before it plus 17, which is 36. So I guess if you had to make the whole table, which you don't in the homework, I think in the homework, it's just they ask for individual cumulative frequencies and things like that. But you could still kind of put them together like this, where this is the easiest way to make the cumulative frequency column, is you just keep adding the new frequency to the last cumulative frequency, right? That way you add up less stuff. So then if we were going to do it like that, then the one after it, 36 plus 19 is 55. Then 55 and 10 is 65. Plus 6 is 71. Plus 4 is 75. Plus 5 is 80. And we should get the total number of observations in the last spot, which we're getting it. And then the cumulative relative frequency, well, we already know this is a 0.1. Then, let's see, 19 out of 80, that's in here somewhere already. Oh, it's right here, 0.2375. All right, 2375. Then let's see, 36, that's 0.45. 55 is 0.6875. Then 0.8125 for 65 over 80. 71 over 80 is 8875. 75 over 80 is 9375. And the last one's a 1. All right, that's 80 over 80. Okay, so we got it, whole table. All right, I think as far as the frequency table goes, that's everything that you can do, pretty much. So now, moving on to histograms, the graphs. So more or less, a histogram is a graph of a frequency table. Right? Like if you have the frequency table, it's really easy to turn that into a histogram. Because then you've got your classes set up and you've got your frequencies, which basically tell you how tall the bars have to be. So that's really what it is. If you want to think the histogram is basically if you took the frequency table and graphed it. Yeah, that's what it is. You could also do it with a relative frequency table. The graph looks the same, but the y-axis is calibrated differently. And we're actually going to see that in, I don't know, 90 seconds. But let's see. So a histogram is a graph for a quantitative variable, and it's supposed to show how the values are distributed of that quantitative variable. Let's see, the book used a big word here, or the Newton notes. I think they have adjoining in parentheses, but they use a big word. I forget what word they use. I liked it. It's too bad I can't remember it now. But then each bar represents either a value or a class, depending on what kind of data you have, right? Like if it's the number of cars, it's going to be where each bar is a value. If it's this with these monthly salaries, then it's going to be a class for each bar. And then with a frequency histogram, which I guess would be a frequency distribution turned into a graph, then you would look at your frequency table, and then whatever the frequency is, that tells you how tall you have to make the bar. And then with the relative frequency histogram, you can do the same sort of thing. You would basically be making the same graph. It's just that then the y-axis is going to have proportions on it instead of counts. But the graph would look the same, like it would have the same shape. And you can also do this with the cumulative frequency and the cumulative relative frequency. That's less common, but you could make one if you wanted to, and it would basically be the same procedure. All right, so let's see what they look like. So a frequency histogram for the cars. So they're like, notice, so we have the bars all touching each other, right? And then we've got a bar for 0, bar for 1, 2, 3, 4, and 5. And then the height of the bar is just based on what the frequency was, right? So for 0, the frequency was 3, right? So that's the height of this bar. For 1, it was 13. For 2, it was 16. For 3, it was 5. And then 2, and then 1, right? And so that's it. And another reason to keep the class widths all the same is that then when you make the graph, the only thing that varies is the height, right? Because then all the widths are consistent. And I know that doesn't really matter here because these are all individual values. But I'm thinking of it now, so I just wanted to make sure I got this part in because I'm kind of improvising it. The reason you want to keep all the class widths the same is then if all of the widths are identical, the only variation is height, then your eye is going to reflexively view the differences between the bars correctly. If the class widths are different sizes, then your eye is naturally going to be drawn to differences in area rather than just one dimension at a time, and that messes things up, right? So frequency histogram, okay, what about a relative frequency histogram? And I guess think about, like, just maybe just temporarily remember what that graph looks like, because the other one looks just like it, right? The only thing that's different is what's on the y-axis, right? Like if you look over here, they're all proportions instead of counts, right? There's 3 over 40, the 0.075, right? That kind of thing, right? There's 0.325 for 13 over 40, right? That's what we've got here. So same graph, right? I mean, it kind of comes down to a matter of preference if you would rather have a frequency histogram or a relative frequency one, at least like in real life if you're putting a presentation together, right? Like they're the same graph. You're seeing the same stuff. So then it becomes kind of an aesthetic difference, I guess. I think most people usually go for the frequency one because the counts feel a little bit more direct, and I'm on that team too, I think. But there are cases where maybe the relative frequency histogram ends up being more relevant for something else that shows up later, right? That seems like it would make sense. But yeah, they're about the same graph. Okay, another thing I wanted to bring up is notice how here the x-axis just says the 0, 1, 2, 3, 4, 5. There is an alternate labeling, and this shows up in the homework. Another thing that you could do is instead of having 0, 1, 2, 3, 4, 5 underneath, basically what I have labeled here is the midpoints between 0 and 1 and between 1 and 2 and 2 and 3 and so forth, right? Halfway between 0 and 1 is a half, right? So that's the boundary between the 0 bar and the 1 bar. Then halfway between 1 and 2 is 1.5, so that's the boundary between the 1 bar and the 2 bar. Halfway between 2 and 3 is 2.5. That's the boundary between the 2 bar and the 3 bar and so forth. It looks weird to have a negative 0.5 over here on the other end, but I mean, considering that a negative number of cars owned is not really a possible value, but you know, to kind of go with the way that the rest of this is set up to keep the same width, that's the number that ends up there. So it looks weird, but it's actually fine. And there's nothing wrong with calibrating the axis this way or calibrating it this way with the 0, 1, 2, 3, 4, 5. They both work. But I did want to bring up this alternate version because it shows up in the homework. Not every single time, but it does show up. So I wanted to throw that in. But then also, the software that I used for the two graphs on this page is different. I think, let me go back up for a second. These are Excel graphs, definitely. That was what I used there. To get a histogram to look good in Excel, there are actually like extra little tricks that you have to do, because usually they don't look that great, but I don't know. I actually don't know the tricks for the newer versions of Excel. I had to use Excel 2010 to get them to look this decent. Because the big thing is that it's hard to get the bars to touch. You have to know what you're doing. Like, you have to go into Excel a little bit to make that happen. But then this is done in StatCrunch, which is actually the software for 167, for MAT 167. And so is this. Because in this one, I turned on the show the counts on top of the bars, just because I like that, but also notice how the axes are. So the way that we had the classes set up is that, you know, like this one here is really what, 2600 to 2799, then 2800 to 2999. So what we end up with here, for example, and I guess since everything around this is blue, I should use a different color. So like, what does that come from? And that is halfway between the, I guess, upper class limit on the left, which there would be 29.99, and the lower class limit on the right, which is 3,000. Right, so that's why that number is there, right? It's that the class to the left of it cuts off at 29.99, and the one to the right starts at 3,000. So it just goes halfway between, says, okay, that's the value that's right between those two bars, right? And I intentionally had to skip numbers because these numbers are kind of long, and if they were all in here, it just looked too cluttered. So there would be a 2799.5 right there, and there's a 3199.5, and over here is a 3599.5, right? And then the homework questions tend to be things like, how many values are in between 2999.5 and 3999.5? Then you just go, well, I just have to add up the heights of these two bars. And I don't think in the homework they have the heights sitting on top of them like that. That does make it easier that you could go, oh, well, it's 17 plus 19, so it's 36. But also with StatCrunch, I couldn't have the individual like 11, 12, 13, 14 lines in between there. So that was actually why I made these show up. Because in the homework, all the individual lines, all the horizontal lines are in there, which would make the counting a little bit simpler if you didn't have the numbers up on top. All right, the other thing in this section is something called a stem and leaf plot. This is another graph. It's sort of like a quick and dirty graph. And it functions kind of like a histogram, except you have a little bit less control over what it looks like. But there is an excellent point with stem and leaf plots, which is that you can see all the individual values. So that in theory, if you were given the stem and leaf plot, but you weren't given like a spreadsheet with all the individual data values, you could just make it based on the stem and leaf plot. You could recover the whole thing. And you can't do that with a histogram, right? Because notice if I go up to where the original data is for the salaries, we never actually had them. All we had was the classes and the frequencies, right? We don't have the actual individual values, but we could still make the histogram, right? That was okay, right? We have the histogram right there. But if you were given this histogram, you wouldn't be able to reconstruct the data set entirely, right? Like for this last class right here, you could say, okay, fine. There are 5 of them in that last class from 4,000 to 4,199, right? Okay, well, we don't know exactly what those 5 values are, right? And there's no way we could figure it out. We just know that there are 5 of them in there. And that's as far as you could go. But with a stem and leaf plot, you could actually bring out the whole thing. But we're actually going to go forwards rather than backwards here. So the way that you would construct one is that you got to break every data point into a stem and a leaf. Usually it's that the leaf is the last digit and anything before it's part of the stem, which is basically what it says right there. Although sometimes you round off first, like if the numbers are really long, then sometimes for accessibility, you round off, and instead of having it in ones, maybe you have it in thousands or in millions or something. And so then that way you get a stem and leaf plot that's this long instead of a stem and leaf plot that's this long. The drawbacks are that you don't really get to control how wide the classes are. And also that for a big data set, these things look really nasty. They're good for a small data set. I do have an example in here of what happens if you do it with a big data set, but we'll get there in a few minutes, I guess. So we also have, I guess, a common thread with the examples that they're about trucking, because now we have the ages of 40 truck drivers employed by a trucking company. I kind of did that on purpose, but kind of didn't. I wrote that one and then I went, oh, look, it matches the other one. I should use this one. Because I had a couple of different versions here, but I kind of like having the consistency. But anyway, if you're going to make a stem and leaf plot, these are all 2-digit numbers. So the way it's going to work is that whatever's in the ones digit is going to be the leaf. Whatever's in the tens digit is going to be part of the stem. So like for the 26, the 6 is going to be the leaf, the 2 is going to be part of the stem. For 34, the 4 is going to be the leaf, the 3 is going to be part of the stem. That kind of thing. But first of all, we got to figure out how to make the stem. Like where do we start, where do we stop? So in order to do that, we got to figure out the largest and smallest values. All right, combing through this, there are a few that start with a 1. It looks like the smallest one is right there, the 18. The biggest, I think, is 52. There's a 51, there's a 50. Yeah, right. So when I make this stem, I'm just going to go 1, 2, 3, 4, 5, like that. So I guess I could kind of diagram this, like for the 26, what we're going to have is 6 is going to be the leaf, and maybe purple, brown, that'll stand out more. The 2 is going to be part of the stem. So watch what I do here. So for the 26, let's see. Yeah, I'll make the leaves a different color. Why not? I'm just going to put it in like that. There's the 26. Now it's in the stem and leaf plot. Right? Because then that leaf of 6 means, oh, well, we got a leaf of 6 with a stem of 2. So that means that the data point must have been 26. Then for 34, I just need to put a 4 where the stem of 3 is. Then 22. You can see what's going to happen here, right? 45, 37, 30, 19, 26, 34, 20. All right, and I guess this will take a little while since there are 40 points. But we're going to have 32, 43, 51, 50, 40, 44, 45, 36, 35, 42, 49, 38, 26, 28, 37, 42, 40, 38, 32, 43, 41. Sorry this is trailing up. 23, 18, 19, 26, 52, 43, 37, 4750. Okay. That's halfway there. Because basically all I did here was that I got the leaves in the appropriate lines. And I guess if you want to count them up to make sure, then you should have 40 leaves since there are 40 data points, right? So let's see, 3, 4, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 1, 2, 3, 4, 5, 6, I hope I miscounted here. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 30, 1, 2, 3, 4, 5, 6. Okay, we're good. The thing that you want, which I don't have right now, is that you want the leaves to be written in increasing order. So because there are 40 data, I mean, if it was, like 15 data points, maybe you can jump to having them in order right away. But with 40, I thought it made more sense to have an intermediate step where we just got all the leaves in the correct rows, and then we can actually put them where they're supposed to go. Okay. Give myself a little more room here. Okay, so the first one's easy, right? Because you go, well, that's 8, then it's 9, then it's 9. And actually, I'm going to start crossing stuff out. So I should do these in black. So I can cross them out in black up above. Because for the 8, 9, 9, we can just see it. But then for some of these, it's easier to start crossing things out. So like, okay, we got all 3 of those. Then 0 is the first one in the next row. Next digits, there's a 2, then there's a 3. I guess I can put those in there. So 2, 3. Then 4 6s. 1, 2, 3, 4. So you would put them all in here. So make sure you include repeats. This isn't like set theory, where then you wouldn't. Right? In that data set, there were 4 26s. Right? So since 26 shows up 4 times, you need 4 of that leaf of 6 to show up in here. So that's what that would mean, right? Like if you didn't have the data set, but you were just given the stem and leaf plot, and you saw the 4 6s in there, you'd go, oh, that means there are 4 26s in the data set, because those 6s are in the row that goes with the 2 on the step. So they must be 26s. Then for the 30s, let's see, we've got a 0, and we have 2 2s, all right. 0, 2, 2. Do we have a 3? No, we do not. A couple of 4s. Get them in there. Then, let's see, a 5, a 6, 1, 2, 3 7s, and then 2 8s. Okay, I can remember that. 7, 7, 7, 8, 8. Then for the 40s, let's see, a couple of 0s, then a 1. Then, let's see, a couple of 2s. Then 1, 2, 3 3s. Then a 4, and then 2 5s, and then a 7 and a 9. Okay. 4, 2 5s, 7, 9. There we go. And then the last one's easy, right? 0, 0, 1, 2 when they're in order. All right, got them all. Okay, so then that would be like right there. If you had to construct one, this is a correct stem and leaf plot. So then that one would be a final answer. But you don't have to actually construct one in the homework. They ask for things like, true or false, or I guess it's rather than just one of them, it's like, which of these 4 statements are true? And it'll say things like, there are 3 37s, which is true, right? There are 3 of those. And then it'll say, there are 4 19s, and then that's false because there are only 2 19s, right? Those 2 9s right there. It tends to be stuff like that. But I think if you can go from the data set to having the correct stem and leaf plot, then you would know what the leaves are, right? Like you go, oh, 343s, 245s, 250s, 152, right? You can see all that in there if you know how they're made. So then those questions that are about, how many 26s are there, how many 19s are there, then those become a little more straightforward, I think. But that, I believe, that's just about it for this example. There's a little bit more stuff in here, though. I wanted to have an example that did show the data values being rounded off to make the stem and leaf plot, which is what's going on here. The software I used here, by the way, is a software called R, which we are not going to get into because it uses a command line, which you can sort of tell from that thing that's in red up there. But this was in there, and it was easy for me to get this to look the right way. So I used a bunch of different software to make this thing. But these values are so big. Right, like you've got these values that are 6 digits long because Alaska is huge and Texas is huge, right? And in I think that's Montana. These two in some order are Montana and California. I forget which. I know those are really close to each other. I mean, obviously the big one is Alaska, right? It has to be, and then that one's Texas. But yeah, you got some really huge numbers, and you couldn't do it just saying like, well, we're going to have a 4 as the leaf and a 103 as the stem, and then eventually we're going to have a 1 as the leaf and a 57064 as the stem. That stem and leaf plot is preposterously huge. And that doesn't help, right? You want something that's sort of compact that you could look at all at once, right? That would be relatively small. And then maybe you could see things like shape and if there are outliers and that kind of thing. So it's going to be easier if the numbers are rounded off. So the thing that I did was that I wrote the numbers in 10,000s and rounded them off. So the Alaska number, the 570,641, so in 10,000s it's 57.0641, just rounded off to 57. And you can see it down here at the bottom, right, where the stem's a 5, and there's the 7. And then the 155,779, which I think is Montana, but it could be California. I'm about 60-40 on which is which. It's 15.5779, which then would round up to 16. So it's that 6 right there. Also, notice that the stems are split, where it's like the first half of the zeros and then the second half, right? It's like 0 through 4 and then 5 through 9. And then they're all kind of written like that. That's one thing that you can do if one of these ends up being really long, which if that split wasn't in there, then the 0 stem would go like way over here, right? So this is a little bit better. So that's the one thing you could do to kind of adjust your class with, is instead of just having 0 row, 1 row, 2 row, you could have first half of 0, second half of 0, first half of 1, second half of 1, and so forth. And that's what's going on here. And R just did that. Like that's built into it to make this a little bit more accessible, I guess. And then notice you got big gaps, which we didn't have before, right? Like there's nothing starting with a 2 that would then have a 0, 1, 2, 3, or 4. Nothing starting with a 3, 4, or a 4, or first half of 5, right? And so then you just have these gaps where there's no leaf. And then the 57, right, the Alaska number, that's clearly an outlier, right? Like that's way bigger than everything else. I don't know about Texas. That's kind of borderline, because even though we haven't gotten into this yet, you could argue that this still kind of fits into the overall pattern. It's not that weird, but this is way out there by itself, right? Definitely an outlier. All right, so that's one where they're rounded off. And then the other example I wanted to have was, what happens if you do it for a giant data set? I also did this one in R, and I had to make it really tiny to get the effect. So even if the digits aren't that readable, you can see it's 0, 0, 1, 1, 2, 2, 3, 3 on the stem. This second 0 row, it's got a whole bunch of 6s, then 7s. It's actually not done. And then there are a bunch of 8s and 9s. It just keeps going and going and going. So this really just doesn't work, right? You can't even fit it on the page. You can't even get close. I mean, look how small my font is. and it's not even close to fitting on the page. And this is why this doesn't work that well with large data sets. The thing that's nice about the stem and leaf plot, that you can recover the entire data set from it, that also makes it tough to work with large data sets because every value in the data set has to have a leaf, right? Like there's a digit for the leaf for every single value, and if there are lots of those values, then the size of this thing, at least like horizontally, is going to get out of control, right? And that's what's going on here. It's just way too wide. And if you have a big data set, you're just generally better off with a histogram. And you wouldn't really even like that extra thing of, if you have a stem and leaf plot, then you can recover the original data set if you didn't have it. With a huge data set, that would take forever anyway, so you probably wouldn't do it, right? I mean, that's going to be helpful if your data set's kind of small, but when it's huge, I don't know if that's a thing that would really happen anyway. And this one does also have the split stems. I put this down here, although it also applies to this one up here with the state areas. Okay, they don't work too well with large data sets, right? That's the whole point of this thing, and that's also the end of 3B. I think that would basically cover everything. The format of the questions is a little bit different in the homework than some of the stuff that I put in here, because in the homework you don't really construct stuff, right? Like you have to pick the best histogram out of the lineup, or you end up counting up how many values are between two specified numbers based on how tall the bars in the histogram are, things like that. So the phrasing or the perspective is a little bit different, but it's this stuff. And I think if you know how they're made, then reading them is actually easier than making them. I think hopefully that was the right way to go about this.